Titration is an experiment in which a substance of known concentration is added to another one to find the concentration of the other substance. Here we will discuss acid-base titration, which is usually done by adding a base to an acid and sometimes by adding an acid to a base. And this titration can be done in two ways. Okay, the first one of them is by using what's called uh, acid-base indicators. And these acid-base indicators are compounds that change their color at a certain pH range, and we want that pH range to include the equivalence point for that reaction. We're gonna discuss equivalence point later in this video, and from the reaction we can find the concentration and maybe the Ka or Kb values that we want. The other type or the other way is by using pH meters. And by using pH meters, we find the pH value of the solution after adding a certain amount of the base to the acid or the acid to the base. Then we can take these values and plot the pH as a function of added volume of titrant. For example, if we are talking about titrating HCl with NaOH, we will have this y-axis having the pH, okay, and the x-axis having volume of NaOH. But for the sake of simplicity, I'll take its equivalence of NaOH, which is easier. Okay, the curve can take three general shapes. We will discuss each one. The first one is strong acid, strong base. The second one is weak acid, which is the first one is titrating an acid with a base. The second one is titrating a weak acid with a strong base. And the last one is a weak polyprotic acid with a strong base. Okay, or we can flip them, so we are titrating a strong base with a strong acid and so on. So let's get started. Starting with the simplest one, which is titrating a strong acid with a strong base, we will take in our example 0.1 molar concentration of HCl and 0.1 molar concentration of NaOH. We want to draw the titration curve of this titration. The y-axis will be for pH and the x-axis will be for equivalence of NaOH. Okay. The first point of this reaction will depend on the concentration of HCl we already have. So in this case, we have 0.1 concentration of HCl, which means that we have 0.1 concentration of H plus in the solution. So we make the negative logarithm of 0.1, and it is 1. So the pH is 1, the starting pH is 1. Okay, as we are adding the base, the pH barely rise or slowly rises until a certain point where it sharply increases to the basic area and then going back to a plateau phase where it barely changes. Okay, this region, the first region, which is the plateau, the acidic plateau, let's name it, is because we are adding NaOH, yes, but the NaOH we are adding is being neutralized by the HCl already there. For example, at this point, let me change the color. At this point, we have zero point 0.6 equivalents of NaOH, which means that since we are having zero point 0.1 molar concentration of HCl, here we have added 0.06 concentration of NaOH, or no, 0.06 moles of NaOH. So let's say that the volume is 1 liter by default. Okay, it is 0.1 mole HCl, and we have added 0.06 moles of uh, NaOH. These ones will react with each other, and we will end up with 0.04 moles of HCl. And now to calculate the volume of added NaOH, it is 0 0.6 equivalents will be in 0.6 liters, okay, because both are having the same molarity. So the volume will be added, the final volume will be 1.6. And in order to calculate the pH, we use the concentration of HCl, 0.04 divided by 1.6 will equal 0.025. This is the concentration of HCl. HCl concentration. The pH will be the negative logarithm of 0.025, and it will equal to 1.6. So here the pH will equal to 1.6, although we have added 0.6 equivalents of NaOH, because all the NaOH has been neutralized by the HCl, and its conjugate acid, that of NaOH, is weakly basic. Is very weakly basic. The conjugate acids of strong acids are very weak bases that we neglect their basicity, and the same for acids. Now, getting to the equivalence point, this point is called the equivalence point. It is the point at which we add equal amount of NaOH, equal moles of NaOH to the solution, to the HCl, to the moles of HCl in the solution. Here, all the HCl will react with the NaOH, so that we are only left with the Cl minus and the Na plus. So here we only have Cl minus and Na plus. The H plus and the OH minus will react to form water. And again, because the Cl minus is a conjugate base of a strong acid, it is weakly acidic, and the Na plus is a conjugate acid of a strong base, so it is weakly acidic. The pH will be 7. pH will be 7 because they have neglected acidity and basicity. Okay. By continuing the reaction, we, for example here, where we added 1.2 equivalents of NaOH, we will end up with 2 NaOH excess, and that excess NaOH will determine the pH at that point. So it is a solution in which we have 0.2 moles of NaOH, because all the HCl had reacted and reacted with one equivalent of NaOH, which is 0.1 mole. So we will end up with 0.02 moles, which are the excess of NaOH in the reaction. And the total volume will equal to 1 plus 1.2, which is 2.2. And from here we can calculate the pH, which will be close to 13, because the final point, or the uppermost number we can reach, the uppermost pH, would be 13, because we are dealing with 0.1 molar concentration of NaOH. If it was 1, then we will reach 14. Now, if this curve was volumes of NaOH, it will have the same concept, the same calculations, almost the same calculations. There will be a very little slight change in the calculations, but the final outcome is the same. It's just that equivalence is easier to understand and to draw as curves. Now, the characteristics of this curve are a sharp change here around the equivalence point. It is very sharp, that covers a large pH range, and also the equivalent point having a neutral pH is also a characteristic for uh, titrating strong acid with strong bases, since the conjugate acids and bases are weakly acidic or basic, very, very weakly. Now, going to the next type, which is titrating a weak acid with a strong base. It has the same concept, but we are only dealing with a weak acid. Let's say that we are working with a weak acid that has a Ka value of 10 to the 4 to the negative 4, and its concentration is 0.01 as their 0.1 concentration, molar concentration, and we are adding NaOH to it, 0.1 molar concentration of NaOH. The same as there, the first point in the curve will depend on the initial concentration of the acid. But here, since it is a weak acid, it will also depend on the Ka value. So to solve it, let us draw our ICE table. First, the reaction would be the weak acid, which is Ha, and it becomes in water A minus and H plus. And then draw the arrows to be like this. Okay. The initial concentration of HA will be 0.1, and A minus will be 0. This will be 0. Then we will have 0.1 minus X, X, X. We will end up with, or this is minus X. Okay, that's changed. At equilibrium, it will be 1 minus X, 0.1 minus X, and X and X. So to calculate it, remember that the Ka equals the product over the reactants. So the Ka, which is 10 to the negative 4, will equal to x squared to the 2 divided by 0.1. Okay, we can make it divided by 0.1 minus x, but let's assume that the x is way too much small and we can just delete it. Okay, let's draw it. We'll have initial pH of 2.4 or 2.5. Here we have 2.5. Okay, it will start here. Rise slowly to a plateau phase, then rise again slowly here at the equivalence point, and then like this. If you notice, this is more smooth or smoother than this one, and there is a slight change here, and it is not a complete change. It is not like this. It is still resisting the change in pH, and it is most effective in this and around this point. Let me color it red. Okay, around this point. This point is called the mid-equivalence point, or the inflection point of this curve, at which the concentration of the acid equals the concentration of its conjugate base. So here we have equal concentration of acid, Ha, equals A minus. And if you remember, at this point, when we have equal concentration of an acid and its equal base, the pKa equals the pH. We know that the Ka of this acid is this, and the pKa of it is 4, so the pH here at this equivalence point will equal to the pKa, which will equal to the to 4, to the pKa. And also remember, in a solution where we have a constant, where we have an acid and its conjugate base, it is called a buffer solution. So this is a buffering solution. It has its buffering range around here. Okay, a pH above 4 and a pH below 4. Color that, yes, color, and uh, okay, cool. Okay, let's say that this is 5 and this is 3. Okay, so this would be 5, 5, and this would be a 3. This is the pH, the buffering range of this curve, of this buffering system. What's special here that if we want to calculate the pH at a certain point here, let's say at this point, let me change the color to blue one. Okay, at this point where we have added 0.3, for example, 0.3 equivalent, and this point is 0.5 equivalent. This point is 0.5 equivalent. And that's why it is called the mid-equivalent point. It is in the middle between two equivalent points or between the initial and equivalent point. So to calculate it, we know that here we will have 0.07 of the weak acid of HA, and we will have 0.03 of the A minus of the conjugate base, because since we have added 0.3 NaOH, it will use 0.3 moles of HA and will make 0.3 moles of the conjugate base in this reaction. We write it here. And now by using the equation, the Henderson-Hasselbalch equation, we find that okay, the pH equals 4, which is the pKa, plus the logarithm of the base, which is 0.03 divided by 0.07, which will equal to 3.63. If we do not use the Hasselbalch equation, okay, or we want to do it without assumption, we will do it this way, okay. HA with or without with, it becomes, okay, it becomes A minus and H plus, H positive with the arrows like this, okay. But here we are starting with, okay, with 0.7 moles of HA, and here we are starting with 0.3 and 0. Then the change would be minus x, 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 oh, okay, x. Then at the equilibrium it would be 0.7 minus x, 0.3 plus x, x. And solve it the way we solved this one previously. If you solve it, you will find that the assumption is true, and you will have the same value here. It is common to use Henderson-Hasselbalch equation for buffering because it is more convenient to use. Now moving to the equivalence point here, okay, it is where all the base had neutralized the acid, and we are only having the conjugate acid and the conjugate base. So we are only having Na plus and A minus. Of course, Na plus is a very weak conjugate acid, but A minus is only a weak conjugate base that can react with water to form OH minus. So the reaction at this point will be that, okay, we don't have NaOH, we don't have HA, we only have A minus, and the concentration here will equal the initial concentration here. We started with 0.1 molar concentration, and so we will end up with 0.1 molar concentration. Okay, this will react with water, okay, to become, okay, with H2O, H2O to become OH minus and HA, and HA. Okay, so the initial will be 0.1, the water is, okay, in excess, so OH minus will be 0, okay, and HA will be 0. We are not having the acid here. The change would be minus x, okay, minus x, 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 and here we will have 0.1 minus x, x, x. Okay, I'm going to draw the arrows here. Okay, and solve it as any problem of acids and bases. I won't solve it here, but just to point, the pH here will be higher than 7. So it is not neutral because this A minus is a weak base that, as we said, reacts with water to form OH minus. So it will increase the pH of the water or of the solution. The last part of this titration curve is also determined by the concentration of NaOH, so it doesn't give any information about the substance being titrated, so it is common to not to find it, so it is common to delete it. So you usually find titration curves like this and in the equivalence point. The characteristics of this curve are that it is smooth here, it is smooth, it is not just like this, it is like this and changes sharply. No, it is changing progressively and smooth around the equivalence point, or at least smoother than this one. Okay, and has an equivalence point that is basic. It's pH here, the pH, right there. The pH is higher than 7 because we are titrating an acid. Okay, and now to the final one, which is titrating a weak polyprotic acid with a strong base. It is similar to this. So to the cut this. It is similar to this, so I will continue drawing here. Okay, the difference is that we are here dealing with an H2A. It can lose 2 protons, not 1, 2 protons, or 3 or 4 or 5. I'll draw here the 2 protons, and more protons, more repetition. So it is repeating this part like this. Smoothly, but two phase, or smoothly, almost two phase, then high. Okay, since this is a diprotic acid, here the last part will be determined by the base again. So we have a concentration of 0.1 NaOH. It will be 13. This will be 13. Again, it is common to be deleted. Let's say that this acid, this diprotic acid, has the first Ka as this, 10 to the negative 4, and the second Ka2, okay, Ka2, let me write it here, Ka1 equals, and Ka2 equals 10 to the negative 9, So that the equivalence, the second mid-equivalence point, or the second inflection point here will have a pH of 9. Okay, the pH here, let me draw the same color, will be 9. Okay, here it was 4 because the Ka1 is 4. What's special about this titration curve is that the equivalence point here can be calculated by taking the average of these two points. So this is 9, this is 4. 9 plus 4, 13 divided by 2 will equal to 6.2, 6.5. Okay, if you notice, okay, this is the equivalence point for me. Right, an arrow, okay? This is 6.5. If you notice that this is not greater than 7, and that's possible here because the electrolytes here are not Na and A minus, they are Na positive, okay, sodium ion, and Ha minus. This Ha minus is called an amphiprotic substance that can act as an acid or as a base. So in this case, it acts as a base more than an acid, and it acts as an acid more than a base. So yes, it is possible. It is not a must to have the pH at the first equivalence point be greater than 7, unlike the one we discussed just previously. Okay, the first equivalence point will be reached at 1 equivalence. The second mid-equivalence point will be reached at 1.5 equivalence. The last equivalence point will be reached at 2 equivalence. So we need 2 equivalents of NaOH to completely deprotonate or equilibrate the acid in the solution. So the last equivalent point will be right here. Okay. Green, okay, right here, and its value can be calculated by calculating the pH of the substance still there, which is A minus minus. We know that the pKa of its conjugate acid is 10 to the negative 9, so its pKb is 10 to the its Kb 10 to the negative 3. 10 to the negative 5, 10 to the negative 5, and pKb will be equal to 5. Okay, from there we can calculate it as any weak base in a solution. And it will have a value of 11 here. Okay, so this has a value of 11. Okay, 11. Yeah, like this. If this was a triprotic acid, it will have additional repetition here. Okay, this will be more smooth. Let me delete this. This will be more smoother, not more smooth, smoother, like this, like this, and get up then to the part determined by the NaOH. So it's the same concept. In the next video, I will talk about the titration curves of amino acids, which are like an ID card for amino acids. You have to know that each group of amino acids have a certain characteristics of titration curves. Some amino acids are triprotic and others are diprotic. I'll talk them in that video. And also keep in mind reading the PDF I included with for this video series. It contains explanation for what we discussed here, also with titration curves that are more organized than these ones here I drawn now. Thank you for watching and good luck in your study.